Okay, again, just to set the problem. Okay, water level in a bucket, much like the bucket that I have right here. If I poke a hole in the side, changes with respect to time. Water level is Y, time T. Water level is going to change with respect to T. The water is going to go down more and more slowly. You can take something that's more or less cylindrical, poke a hole in it, and watch the water level go down. And don't do that with your fine china. It's hard to poke a hole in fine china. It tends to shatter. And you probably don't want a hole in your fine china anyway. But anyhow, you do this, and water level changes more and more slowly so that the graph of water level versus time looks like this. Now, we're not going to do the physics, but if you do the physics, physics predicts that, well, first the pressure is proportional to the depth, and then energy considerations, kinetic potential energy changes, tell you that the rate at which the water flows out should be proportional to the square root of the pressure, and therefore to the square root of the depth. Now, you don't have to know that, but that's the physics reasoning. Okay, that's kind of interesting, and if you have physics in your future, doesn't hurt to think a little bit about it, but you're not going to be tested in the physics. But this is a prediction, and then using some more advanced mathematics, actually a very simple differential equation, but something you don't get to until you've had at least a year of calculus. Maybe at the end of your first year of calculus, you would be in shape to solve this differential equation. So then, at this point, that differential equation is just kind of a miracle. So we can say a miracle occurs and we conclude that y is a quadratic function of t. Okay, so you can kind of ignore how we get the miracle to occur because that's a little bit more advanced. If you take a rigorous calculus course next year, because you probably want to take the second semester of this course before you do a rigorous calculus course, if you happen to be on the path to that sort of thing, then at the end of next year, spring 2022, you'll be able to do the miracle. Okay. And if not, appreciate the fact there's a miracle out there that's not that deep. But you've got a little ways to go before you get to it. Okay. What good is that, and what does that tell us about this course? Well, first you got this proportionality statement here, but you got to incorporate that into the miracle, and you don't know exactly how to do that. The application here if y is a quadratic function of t, then that means y equals at squared plus bt plus c for some a, b, and c. And that means if we find this function, we could, for example, predict the vertex of this parabolic graph, because this graph is now parabolic. It's a parabola, just to remind you, axis of symmetry. I have two M's in there. I don't know what I've got there. Axis of symmetry. This. Maybe some zeros. Okay, now if you measure your depth from the bottom of the bucket, y is never going to be 0, because once you get to the level of the hole, it's going to stop flowing out. If you measure y from the top of the bucket, well, it's never going to be 0 because the water's never at the top of the bucket. If you measure y from somewhere between the hole and the water level, then you could have zeros. So where you measure y from determines whether this graph stays below the axis, x-axis, above the x-axis, or goes through the x-axis. Now, one thing that doesn't happen is this thing's a parabola, but this part of the parabola is irrelevant. Okay? So you have the relevant part of the parabola, and I'm not sure how well this yellow contrasts on the video, so let's go ahead and make it a yellowish blue or whatever you want to call that. Kind of green, right? Okay, so this part of the parabola this color shows up well. Well, that's kind of bad, but okay. This part of the parabola models the water level. This part doesn't happen. Doesn't happen because the water doesn't start rising after it gets down here. It just stops. So the thing stops right here. So the domain of this function the domain of the model is just this part of the t-axis. Now what's that have to do with simultaneous equations, because that's where we're heading. You've done simultaneous equations, 2 equations and 2 unknowns. This is going to lead us to simultaneous equation in 3 unknowns. Okay, so here we have observations. Okay, I do this with my classes. If we were in class, we would have picked a nice day, and of course this class ran from September, so we just pick any decent day in September, and we don't use a bucket, but we take a 3-liter soft drink bottle that's marked off with a scale, and we have a hole in it, and there's a little tube coming out of that hole. We fill it with water, and we time it. And it's kind of entertaining because we time it by having the whole group walk around a circle, pacing at a regular pace, and making a check mark every time they take a step. And we have somebody else who hollers every time the water level gets to a certain mark. So that we get depth versus time data. we know how far those marks are, or we can measure them afterwards. We measure how deep they are relative to whatever point we want to measure from. And we get data that looks like this. The data doesn't follow a perfect parabolic curve because we're doing this by pacing around, and we're trying to keep a steady pace. There's always a tendency to speed up a little bit or slow down a little bit. And there's also a tendency to miss a check mark here and there. Also, when we measure the depths of the marks, we can be off by a little bit. We go up by a millimeter or two, so that we don't have perfect data. And we get a lot of data points because we have a full class, and hopefully, we got 20, 30 people in the class, so we just get this whole band of data points here. Looks something like this. And there's a trend to these data points. So we try to, now you can always go to software and stuff, and yeah, you can go to Excel. You put this stuff into Excel and ask it to do a polynomial degree 2, and it'll give you the best fit line in a sense that I could define, but we don't really have time. I don't like to do that, okay? That's too pat. You don't learn anything from that. What you do is you take this data and you sketch a curve that you think goes kind of through the middle of the data points. Now, you're trying to minimize the sum of the squares of the vertical distances of the point from the line, and that's kind of a mouthful, but if you think about it, you can, I think, interpret that. You don't have to. But in any case, you sketch this curve. Okay? So this is called your trend line. To best predict the reality, because none of these points is reality. These points are observations of reality, and there's uncertainty in any of our observations of reality. But by doing a lot of observations, we can get a very good model of the reality. And that reality, in this case, is dictated by a trend line that's going to be pretty predictable because we get really pretty good data from this thing. Okay, we sketched the trend line. Now, our procedure is we assume that the trend line is parabolic. Which means we have a quadratic equation. And choose 3 points on the line, not 3 data points. Okay, now, I don't remember if it's your text or some other text. It just tells you to pick 3 data points, which is absolutely ridiculous. Okay? And I don't want to get into a big argument with the people that wrote the text, who might well and very likely do know more than I do. Well, maybe not. But I think most textbook authors probably know at least as much as I do, and many of them know a whole lot more. But I would debate this with them, and I don't think they'd change my mind, and I think I'd have a better chance of changing theirs. If you pick 3 data points, you're ignoring all the other information you have. You know, out of a class, we might have 100 data points. Okay? And if you just pick 3 of them, without thinking where the trend line is, it's a real bad idea. It's also a real bad idea to draw your trend line so it goes through any specific data point. You want to follow the trend, not wobble around trying to find data points. You sketch the smooth curve that the trend line or that the data points seem to imply. Okay, so we're trying to get the reality. The reality is the trend line. The data points are just observations of reality. We don't choose data points. We choose 3 points on the line. So I'm going to choose this one, and I'm going to choose this one, and I'm going to choose this one. And we don't want the points to be too close together because we're going to have to estimate their coordinates. And if our estimates are all off by 1/4 of a millimeter, or whatever it is, then it's better that they be far apart, so the 1/4 of a millimeter is a smaller proportion of the stuff that we're looking at. I could say much more about that, and I could make it rigorous, but we space the points out to minimize the effect of errors in estimating our coordinates. Okay, so now we've got 3 points. Now we plug the coordinates into the form y equals at squared plus bt plus c to get 3 simultaneous equations in the parameters A, B, and C. Now I kind of hope I have a better board here, but no I don't. I'll use this one. Okay, well, let's say, for example, let's do some estimates. Okay, let's estimate here. Okay, let's say that y here is 40 and t here is 200. Okay, well, 200's there, 100's here, 150's here, 50's here, and now I can break this. I didn't do a very good job of that, but it's okay, just illustrating. So there's a scale. Here's 40. Halfway is 20, 30 is halfway between, 10 is here, and hopefully we're somewhat familiar with being able to do this. And now I can project this point down here, and it looks like we end up with about 45 here. And I can project over here, and of course there's 30, there's 40, there's 35. I'm going to say this point looks like 45, 37. Now I'm getting myself in trouble because I'm going to have to square some of these numbers. So we know that things are not going to work out as well as they should, but do it anyway. Round numbers would have been better. Okay, and I'm going to say this point looks like it's about 112. I'm going to fudge. I'm going to say 110. And then I'm going to say 18. And then this point, I'm going to say 190, because again, I don't want to have to square 192 or 193. So I'm going to say this point looks like it's about 198. So points on the line are 45, 37, 110, 18, and 198. Checking the camera. Okay, we don't, okay, well now what we want to do is plug these into this form. So we get 0.4537, y is 37, x is 45. 37 should be then a t squared. Well, 45 is t. So this should be 45 squared times a plus 45 times b plus c. Yeah, 45 squared, that's not too hard to square. You're going to get 2025, I think. So we get 2025a plus 45b plus c. Okay, well then the point 110, 18 implies that 18 equals 110 squared a plus 110b plus c. And actually 110 is easy to square. I cheated, made that easy to square. That's 12,100a plus 110b plus c, and 198 okay, 190 squared is 36,100. So we have this. So now we have equations system of three linear equations in the unknowns A, B, and C. And that's what I referred to as our parameters of the model. A, B, and C are the parameters of the general model, okay, of our model. And once we know the values of those parameters, we know our function. We can find its zeros if it has any. We can find its axis of symmetry. We can find its vertex. And we can do calculus with it. Of course, we won't, because we're not there yet. And, you know, the course isn't there yet. So, and this course doesn't get there. So here we have it. So I can write out the system. It's 2025a plus 45b, and it looks like I wrote 4b there instead of 45b, I'll put a 5 in there. Now you can't read it, but you know that's what it says. Plus C equals 37. 12,100A plus 110B plus C equals 18. And 36,100A plus 190B plus C equals 8. Okay, now we have 3 simultaneous equations and 3 unknowns. We can solve this. Okay, and it's actually pretty easy to solve this, easier actually than most systems of 3 equations, because you notice that C is going to be really easy to eliminate. If we just, excuse me, multiply one of the equations by -1 and add it to any of the others, we're going to get an equation that just has A and B. So for example, if we take the first and if we subtract the first equation from the second, or add the -1 times the first equation to the second, C is going to go away. We're going to have an equation with just A and B. And then if we do that with the first and the third equation, or the second and the third, wouldn't matter, either way, we eliminate C and we get a different equation with A and B. Well, now you're just down to 2 equations and 2 unknowns, and you know what to do with that. That number's a little messy, but it's not difficult. So we're going to go ahead and do that.